This is video 4 of looking at volume of solids of revolution. And we're going to take a look at a different type of problem here. So this is a volume where we have two defining functions. And we're going to rotate a region that's formed by those two functions around the x-axis. So this is going back to the first page where we were talking about here. If your region is bounded by two defining functions, then what you're going to have is a sample washer rather than a sample disk. And I think I said that, I was repetitious here, I think I said that here also. All right, so let's draw the picture. That's what the directions say back on the first page. So this one says that we're going to take a region that's between y equals x squared and y equals the square root of x and rotate it around the x-axis. So if we look at the graph of this, here is our graph of x squared. So here's y equals x squared. I mean, we can draw the whole thing here, all right? But our other one is the square root of x, and the square root of x looks like this. And basically they're saying, take this region that's bounded by these two functions, which is this region right here, and rotate that around the x-axis. So I'm going to, again, since we're just looking at this region, I'm going to kind of clean up our graph here, clean up the picture by erasing a lot of this extra stuff. So we're basically going to be looking at this. Okay, again, here's our y equals x squared on the bottom. If we continue that on, here's our y equals square root of x up here. All right, so if I rotate that around the x-axis, then I'm going to end up with this piece being reflected over, so it's going to look like this. And this piece being reflected over, so it's going to kind of look like this. And then our solid is going to be kind of a strange bowl, I guess, where this is the outer part of our bowl right here. And then this is kind of a cutout in our bowl. So when I rotate that piece around, again, picture this kind of rotating around over to here and then coming back, so it would look like this. And then this piece also would rotate around and look like this. And if I picture another one down here, you can hopefully kind of see the three-dimensional object that's being formed there. I'm going to get rid of some of this pink, see if we can see this a little bit better. So if you look at that, and again, especially if you kind of turn your paper sideways, you should be able to see what we call a disc or a washer. All right, if any of you have done any repairs on things with screws and nuts and all that kind of stuff, you might have used a washer. So a washer, you know, just being a cylinder like this with a hole cut out of the middle. So that's essentially the process that we're going to do, is we're going to find the volume of this outer disc or cylinder, and then we're going to find the volume of this inner disc or cylinder, and we're just going to subtract. So that's the process for these. So basically, if we treat this as our sample washer right here, we want to find the volume of that sample washer, and it's going to be the volume of the outer disc minus the volume of the inner. Right, and both of those are going to be in terms of cylinders, so they're both going to be a pi r squared h minus another pi r squared h. Okay, so this is radius 1 and radius 2. All right, so if I just look first at the outer cylinder, right, the one that goes to here, and think about that radius, right, this point right here would be x, and I'm going to call this is the square root function, so I'm going to call that y sub 1, so x y sub 1, and then this point right here is x0, of course. So notice that that outer radius from here to here is y sub 1, so this becomes pi times y sub 1 squared times h, and the height of that disk, because I'm cutting it this way, is going to be dx. All right, then over here, I'm going to have pi times, and my radius 2, so let me just kind of redraw this really fast so that we can talk a little bit better about radius 2. So remember that we've made this cut that goes like this. And radius 1 went all the way from here to here. But now what I want is this inner cylinder that's right here. And so that radius only goes from here to here. Right? So again, this is the hole. We're talking about the radius of the hole that we're cutting out. And so this point right here is going to be x, and because this is on the parabola, I'm going to call that y sub 2. So xy sub 2, and then this is the point x0. So that distance right there is y sub 2. So this becomes pi times y sub 2 squared, again times dx. All right, so now if you notice on this one, this really, we can do a little bit of cleaning up here. So notice that both of these terms have a pi, and they both have a dx. So what I'm going to do is I'm going to factor the pi out in front, and I'm going to factor the dx out in the back, just to clean this up. And so what I'm left with in the middle is y sub 1 squared minus y sub 2 squared. Now, what we said is that, so that I'm still working on dv, what we said is that if this is x, that we really want this in terms of x also, all right? And so I want you to go ahead and put this in terms of x. So this is going to be pi times, our y sub 1, remember, was the square root of x. So we get the square root of x squared minus, and then our y sub 2 was x squared. So we get x squared squared. And so this becomes pi times, I maybe don't need these squared off brackets anymore because I'm going to simplify these. So the square root of x squared is just x, and then x squared squared is x to the 4th. So that's going to be the sample disk that's in the middle. So now if we want the entire volume, remember then we have to set up an integral because we're going to take infinitely many of these disks and add them up and let the width go to 0. And how do we do that? We do it with an integral. So this becomes pi times x minus x to the 4th dx. And now we need the limits of integration. So because this is all in terms of x, these need to be x values right here. So we need to think about where we're making those cuts. So when we make the first cut, because we're going horizontally, or we're making vertical cuts, but we're moving horizontally, we make the first cut here at x equals 0. So that's easy. Then we make the last cut. So we make all these cuts until we reach to here, and that's our last x value. But we need to know what that intersection point is. So, you know, you might know just by inspection that that's the point 1, 1. Or if you needed to, if it was a more complicated equation, then you would solve the system of equations. So we would be looking at where is x squared equal to the square root of x. So if I square both sides, I get x to the 4th is equal to x. So x to the 4th minus x is equal to 0. If I factor out the x, I get x times x cubed minus 1 is equal to 0. This is the difference of 2 cubes, so that'll factor again as x minus 1 times x squared plus x plus 1. Remember, that's the SOAP thing. Same sign, opposite sign. If this is minus, this is plus, always positive. All right, and then remember that these two are just the cube roots of x and 1. This is just this squared, this is just this squared, and this is just this times this. All right, so anyway, so now if we set those equal to 0, we get x is equal to 0, x is equal to 1, and we don't get any real solutions out of this. So that tells us that these two curves intersect when x is 0 and when x is 1. So that means that that's our other limit of integration, okay? So now, again, just for the practice, let's do this one by hand. And so I'm going to bring the pi out in front. So I have pi times, now we need the antiderivative of this, so that's going to be 1/2 x squared minus 1/5 x to the 5th, evaluated from 0 to 1. And it looks messy, but we're putting 0 and 1 in, so that makes life a little bit easier. So we get pi times, so remember first we sub in the 1, so we get 1/2 times 1 minus 1/5 times 1, minus, then we sub in the 0, so we just get 0 minus 0. So it looks like this is going to become pi times, our common denominator would be 10. So this is 5/10 minus 2/10, which is going to be 3/10 pi, or 3 pi over 10.